Hi, welcome everyone. I appreciate this opportunity to talk about some of the work that we're doing with Dendro-GR. And while this isn't part of the Einstein Toolkit, I have really enjoyed attending this meeting, learning about a lot of the things that are happening in the Einstein Toolkit community in the broader area. We're basically all working on the same type of problems, and we're seeing some of the same challenges. And so it's interesting to share ideas and different approaches on how those can be overcome. Dendro-GR is developed at these 4 universities at BYU and RIT. We have people who are experts in numerical relativity, and the University of Utah and Texas. We have people who are computer scientists. So the Dendro framework is actually developed earlier by computer scientists. It's actually natively a finite element or D cheat code. We've modified it to work with the techniques we use in numerical relativity. This is an exciting time in numerical relativity because there's a lot of development, and this is driven by the new generation or the exciting developments in gravitational wave detection. And the LIGO and Virgo detectors over the next decade we'll have a series of upgrades. The 04 observing run just began a couple months ago or so. And as these detectors are improved and as new detectors come online, they're going to have higher signal to noise ratios. They'll be able to investigate a broader range of possible frequencies, and that will enable us to see a wider range of sources. And some of those that I'm interested in particular are the intermediate mass ratio in spirals and binaries with high spins and eccentricities. In terms of numerical relativity, all of these things in a way pose new challenges, because when you have higher signal to noise ratio, you need higher precision waveforms so that you can extract the science that's available, right, to maximize the scientific output. When we have new bands, sometimes that requires longer run times in the sense of the different time scales to merger. And when you have a larger variety of sources, you need to sample larger regime of the possible binary parameter space. All of these things essentially add greater demands on the waveforms that we produce in numerical relativity. Fortunately, I don't have to say much about that because Deirdre's following me, and she's going to tell us what some of these challenges are specifically in terms of targets that we want to hit, say, over the next decade to maximize the science done with detectors today, and also those coming online like Lisa in the diagram. To tell you, I'm going to talk a little bit about Dendro-GR. I'm going to mention some of the things that make it unique with the wavelets, multi-resolution, some of the tests that we've done, and then I'm going to talk, because I feel like this is really a time for numerical relativists to talk about some of the problems and some of the things. I'm going to talk about just some different ideas that we're working on now. Some of them are probably a little crazy and will be abandoned in a few months, or some of them might develop into something. We'll just have to see. But anyway, so we'll see where it goes and what happens next year. Dendro-GR is our code for numerical relativity. As I mentioned, it's built on the Dendro platform. It provides a sparse unstructured grid. This grid is generated by a wavelet expansion of the functions in a wavelet basis. This naturally produces kind of an octree data structure, and so the Dendro code has a parallel octree that it provides. Then when we actually do calculations, we are able to exploit and use a lot of the current ideas and algorithms that we use all over in numerical relativity. So we share a lot of common features when you get down to calculating things with other GR codes. For example, we can use we basically have blocks of uniform grids, and so we can calculate with finite differences. We can solve the Einstein equations and BSSN type formalisms. We can use standard high resolution shock capturing methods for fluids, whatever needs to be done. So it allows us to build off of, basically 20 years of development in numerical activity and refinement of good practices to give us robust techniques for solving, these equations and getting good accuracy. I want to say a little bit about what's unique about wavelets. And I think if I use them, I can use the mouse here to kind of point. But the basic idea is that we can expand functions in some type of a basis, right? And on the left, I have kind of like a Fourier basis. You can imagine expanding a function on a Fourier basis. And as I go to higher and higher frequencies in my basis, I'm still doing integrals over the entire domain, right? But I can expand the function in that way, and it have some real advantages to doing that. A wavelet basis is a little bit different in the sense that it's constructed from a function with compact support. So in the bottom on the right, I have these are just little representative little functions to show what a wavelet might look like, but there's a mother wavelet function on the bottom row. And then to construct the basis for higher frequencies, I simply take that function and I scale it down by a factor of 2 and I shift it over. And that gives me these other functions that are up here. These are the ones typically called the wavelet basis functions. If I integrate over the region where the basis function is defined, I can get a coefficient, say, in the expansion represented by this dot. And if you look at the rows, there's some places have dots in more than one place. So to make it unique, I get the figure on the right where I remove duplicate points. And I can construct a basis then for expanding my function. It looks like this. On the on the left-hand side, again, something that might look like a Fourier type basis. I have I'm expanding my function in the basis function with coefficients. On the right-hand side, I have an expansion in terms of the wavelet basis functions. Okay. And if I then kind of simplify the figure a little bit here, on the left, kind of those colored blocks show the domain where I would integrate over, and the dots on the right show the locations of where those expansion coefficients live. It turns out that we don't store the functions in the terms of the expansion coefficients. We store just the function values themselves, because when you're doing multiplication, turns out to be much easier. But I wanted to show how the wavelet expansion generates a computational grid. And so this is a grid that we could build. Now, of course, not all of the points may be equally important. And you may have a function that is fairly smooth and a large portion of the grid. And maybe when I calculate the expansion coefficients, I got to find the mouse here, sorry. If I calculate the expansion coefficients here where I've grayed out the color, maybe those are points where those expansion coefficients are very small and almost negligible. And I can choose a scale factor, epsilon. And I could say that if those expansion coefficients are less than epsilon, I'm simply going to remove them, which then gives me the effect of having a coarsened grid. And then I can modify that for doing calculations. Because we have dynamic scenarios, we need to allow the grid to adjust. And so we add in these red points that look like these represent kind of neighboring points. So if I have a wave moving along, I can capture it. But this is basically how we construct the grid in Dendro-GR. And you can see it has a natural tree-like structure, right? So different refinement levels. And at each refinement level, I have a uniform block of points that I can compute on. The Dendro infrastructure provides the parallel octree. And anyway, this just kind of demonstrates ways that data are communicated. Anyway, if I'm going to, for example, compute something on block A here that has points and it has neighbors on either side with maybe different refinement levels. We get ghost points from neighbors with the same refinement level, or we need to maybe interpolate if it's coming from a coarser region. The entire octree then is parallelized with a Hilbert curve. And so this figure on the bottom left shows, like a computational domain, and the different blocks of color show points that would be on, a single process. So it kind of gives us locality in the parallelization of the tree. And occasionally we rebalance the tree to keep things efficient as grids come in and out of the computation. To kind of demonstrate how this works in practice, this is an example of one of the Balsara shock tubes that we did. It's a simple code. You basically see the density, the velocity, and the pressure plotted here for the solution. The real thing I want you to look at is this figure in the lower right-hand corner. This shows the actual points that are used to calculate that solution. So those are the individual grid points that are being plotted there. And on the vertical axis is basically the level of the tree, or moving to more and more refined regions. And you can see the spatial extent of those regions. You can see that this gives us a very efficient grid. A shock tube is a type of problem where you basically either have really smoothly varying things or you have really sharp features, right? And this computational grid does that well. It gives us it refines very, it'll refine forever on a sharp feature, unless you cut it off at some point. And where it's smooth, it coarsens those, takes points away. I want to point out it's, on the right-hand side, we've got a shock that's moving to the right. It's pretty clear why we would have a lot of refinement right there. We've got a discontinuity in the solution. It's going to refine as much as possible there. But notice these other two regions where it's refining on also any point while the solution is continuous at these points, it is not differentiable. So we'll also refine on things that are not differentiable in the solution. The grids that it generates, as I said, are quite efficient. We can get a nice convergence. We can measure convergence both in the sense of, actually, let me back up and say, we can look at how the code behaves both as we change the number of refinement levels that we allow, and as we change that epsilon parameter that determines when we cut off the wavelet expansion. So this figure shows, this turns out this is the hard Balsara shock tube problem, and it's showing the L1 norm, the L1 error and the density function, and the green line that's the furthest to the right shows the error as a function of the number of points that are used in the simulation for having a uniform grid at all of those levels. The other lines are using the wavelet refinement with different values of epsilon. That's remember our cutoff to the wavelet expansion. And so if we set it to be 10 to the minus 6, 10 to the minus 5, or 10 to the minus 4, we get the black, red, or blue lines respectively. And we get a nice kind of accelerated convergence in the error using, it's almost like a factor of 10 fewer points in the simulation. We tested this on a Rayleigh-Taylor, on a relativistic blast wave that generated a Rayleigh-Taylor instability, just because that looked really cool. And basically, this is like a blast wave that propagates out at 0.9 something C. I don't even remember. But this is a picture where you can see these are the actual points used in the calculation. So what I'm plotting here is simply a point, a dot, where a computational point was used. You can see that where I am far away from where something interesting is happening, there are very few dots. As I get closer to where the solution is very dynamic, then suddenly where there's so many dots that it fills in almost like a continuous picture. And you see that the grid adapts very naturally to the features of the solution. So and as this blast wave moves out, those dots come in and out of existence in the computation. This is an older code that we had where we were really parallelizing. We could add a single point in or not. As we go to Dendro, I want to show you what this looks like. Oh, never mind. I forgot. As I changed this from a my PowerPoint to the to the PDF. We've lost the little set of frames here. But anyway, this is a very unimpressive slide showing the small black hole in a 16:1 mass ratio. And I wanted to show you kind of zooming in from the outer boundary to this single black hole, what the entire grid structure looked like. I'll just point out a couple of things. This is the grid for the smallest black hole. You can see that it's very well resolved here. You'll notice that the grids here look a little blockier, or a little more Lego-like than on the previous slide with the blast wave. So Dendro has these leaves of a tree that have a fixed size. I'll mention that again in the future. So basically, instead of pulling in single points at a time, we pull in single leaves of the tree, and you can kind of see how big they are there. Dendro also enforces a 2:1 refinement condition on any, when it refines, it forces a 2:1 condition on the boxes as you move out to coarser regions. Earlier, at the end of last year, the beginning of this year, we finished a series of initial tests with Dendro involving black holes in a vacuum space-time with different mass ratios. We compared our solutions to those given by the LAZEF code for some similar data. These were fairly short runs, somewhere in the order of 4, 6, 8 orbits, something like that, depending on the mass ratio. And these are plots for the mass ratio of 2, 4, 6, and 2, 4, 8, and 16, showing those as comparing those solutions. I'll talk a little bit more about some of these cases. As I said, we can kind of look at convergence in 2 ways. We can increase the depth of the tree or increase the refinement. Or we can also change our scale, our epsilon, our factor that determines how far we expand in the wavelet expansion. On the left, you can see some convergence to the solutions by changing the level of refinement. And here we were changing epsilon from 10 to the -3, 10 to the -5, 10 to the -6 for a q = 1 binary. And just showing, this is plotting the error here, so that you want the difference is going to 0 there. The code is very efficient. It's runs well. This shows the weak scaling on Frontera to about 200,000 cores. And you can see the scale, the timing here is fairly flat. The different colors on the bars tell you basically how much time the code is spent doing different things in communication. There's the yellow line, the right-hand side communication is, or calculation is the red line. The green is the managing the tree and the unstructured grid and filling in points here, which is unfortunately an expensive part, but it also gives us the efficient grid. These plots show the computational resources that we used in a couple cases. So I'm first going to compare to the case on the, talk about the one on the left. So earlier I showed waveforms from a Q equals 8 and a Q equals 16 binary. And this was the number of cores as a function of the computational time that were used in that run. And you can see that initially there's a lot that are being used. I'll mention a little bit more about this later, and it's really going to allude to something that Zach talked about. And but after things settle down, you see that you know, the number of cores drops significantly. And after say time 200, 250 or so, when Q equals 16, we ran on about 500 core, 512 cores. And for the Q equals 8 binary, we ran on 256. And then during the end spiral, that stayed fairly fixed. And then near the end, it would drop or even, you know, further down as the black holes merged and we could course in the grid. The figure on the right shows the time for now always only the Q equals 8 binary and different refinement functions. And this is something I'll say something about. Well, I'm gonna go ahead and talk about it now here. I'm gonna just skip ahead a little bit. And this is something that I think Zach mentioned in his talk earlier this morning. And this shows a Q equals 32 binary. This is a plot of alpha, the lapse, and near the very beginning of the run. And you notice that there's this little ring here about the small black hole, and this ring is expanding. And as Zach showed in his plots, you get this noise from the initial data and the change in the gauges that tends to propagate out. And it scatters off everything in sight. It scatters off the grid, it scatters off of the other black hole. And as I pointed out, wavelets will refine on anything that does not, that's not differentiable. When you have all this noise bouncing around the grid, it's not always differentiable. And so we get a lot of refinement. And so one of the challenges we have is controlling that refinement, because it becomes volume filling refinement, right? As this wave is expanding out, the wavelets are very good to say, hey, there's some new sharp feature of your solution, I better capture it. And they will start putting points everywhere. And so that is what's happening here when you see initially, you know, we jumped from, well, anyway, some small number of cores up to, you know, 3,000 cores, and then it would drop down and drop down as some of that dissipated away. So that is something that we developed some ways to focus the refinements. You know, we basically could tell it we want to focus on just where the black hole positions are. So we developed these kind of ad hoc little functions where we would say, you know, I want epsilon, my parameter that truncates the wavelet expansion, to be small where the black holes are and big when you're far away, especially initially. And then we would, you know, kind of in an ad hoc way adjust this and try to come up with something that was that looked better. And was also, we could had the resources to compute. This is for us, it's still an ongoing problem, and Joseph and one of his students, Chloe, are working on this to try to help us find better ways to do this and to manage it, and to maybe have other diagnostics that can help us, more accurately tell us where the refinement needs to go. The other thing I want to point out is that these runs, once things settle down, they don't use a lot of cores. We did some of these runs with Q=8 binary of 256 cores. Unfortunately, it's not like I can just dial it up and say, I want the answer faster. I want the answer faster. Give me 1,000 or 2,000, or you give me the answer in 3 hours, whatever. I would like to be able to do that, to increase the time to solution, use more cores to get the answer. And for a Q=16 binary, it took us 2 months. So of wall time, 2 months of wall time. But the grids are efficient enough that because these are marching problems, it's difficult to do that. So some of the other work that we're looking at is improving the time to solution. These are kind of this last part of my talk, some of the more kind of areas that we're actively researching, things that we're trying out and may or may not work. One is running on GPUs. We have a version of Dendro that runs on GPUs. We've done some up to Q=8 on the GPU. Melinda Fernando, who did a lot of these, who developed this code, did a lot of performance testing along the way. And in the kind of the upper left plot there, you see the roofline plot for our GPU code. So in this case, all of the data exists on the GPU. The CPUs basically handle communication between different nodes, but we're still memory bound. I don't remember exactly, but earlier in the week we talked about being memory bound versus computationally bound in the calculations. And so that's another thing we hope to address, is trying to push those little dots further up that plot to where we're really using all of the resources on the computer, all of the flops. It's kind of a dirty secret in high performance computing that we build new machines and we say this is a petascale machine, or this is a whatever scale machine, and that number comes from the multiplication of dense matrices with LAPACK. The real live performance, it's actually obtained in most codes, is about 100 times slower, and that's because of the difficulty, all these things that come together between the communication and the bus speeds and all of that, and then how whether you're bound by anyway, many of us are bound by communication timescales. This is some scaling tests of our GPU code. The figure on the left shows the scaling for the CPU code for this particular case, and then the GPU code. So the GPU code is half to, I don't remember exactly, fourth or 40% slow or faster or something, or 60% faster or something. And this was the strong scaling on the GPUs. Another thing that I'm having fun thinking about is how do we improve the precision given the difficulties of doing communication and all of those things. We know that at the end of the day, it's the error budget often and the phase error of the gravitational waveform that is one of the most important things if we want to use our waveforms for data analysis. And if we just naively say, well, I need more precision, let's increase, the order of my finite precision or use more points, that can, sometimes it greatly increases the cost. And so one idea is to imagine, if I have a finite difference stencil there, like on the top left, if I could somehow shrink that down, I do two things. I have a smaller effective delta H, I get more precision. And because it's smaller in size, I may need to communicate less on a parallel computer, which is a benefit. Of course, the problem in this little naive argument is that now I'm using data or points where I have no data, right? I have grid points with the integer values of that index. But there's a way around that, and that's basically based on the PADE expansion or approximation. If I couple the different stencils that are neighboring to one another, then I come up with a system that is, it's now an implicit calculation of the derivative because the derivatives at neighboring points are coupled together. But I can, by doing that, I get more information and I can actually get a higher precision estimation of the derivative. And in 1992, Lele published a paper showing that for fairly simple cases, he calculated them out to 10th order derivatives using just kind of some of these neighboring points. So what does it actually look like in practice? What I have is essentially two big matrices that I build. One is multiplying a column vector of derivatives that the grid points I need them. One is multiplying a column vector of function values. I have a lot of freedom in building this linear system, and I can use that freedom in different ways. I can do it to try to minimize communication and maximize the order of the derivative, or there's some other things that we could talk about. But the point I want to make is that these matrices depend only on the grid structure and not on the functions themselves. And as I mentioned, Dendro has leafs that have a fixed block size. And so actually we only need to calculate these derivative operators one time. And then once I calculate it and I invert the matrix on the left and multiply it by the matrix on the right. I do that once. I save the value. Every time I need a derivative from that point on, I simply just do a matrix vector multiplication, which is very reasonably fast. So that is one thing that I've been playing around with. The nice thing about these compact stencils is if I do an analysis in phase space, I can show that they capture higher frequency modes of a solution much better than the explicit scheme here shown in red. So this red, what this kind of shows is depending on the wavelength of the frequency of modes in a function, an explicit scheme does well at low frequency where it's kind of matching that vertical straight line, the diagonal line that is would be the exact solution. But at high frequencies, it's damping those modes off. At some point, of course, you want to do that, but the compact stencils capture this higher frequency information better. I'm going to skip that in the interest of time. As a fun test problem, I've been looking at the Maxwell equations. I did a run in 2 dimensions of a waveguide, a rectangular waveguide with an odd number of modes in each direction, using a 4th order finite difference scheme, explicit, and a 4th order compact finite difference scheme. This was run at the cutoff frequency, so it's a kind of a true 2-dimensional problem. And this shows the error in the exact solution. The red line is for the explicit standard 4th order operator. It ends early just because I didn't run it as long as I ran the other one. The blue line is for the compact 4th order scheme. You see that it's, in this particular case, roughly 1,000 times more accurate to use the compact scheme. I ran the compact scheme longer just to make sure it never blew up. The other one I'm confident doesn't blow up. So anyway, but that shows kind of the difference in the order of accuracy that you can achieve with a compact finite difference scheme. So recently, Forrest Tsutsa published a paper on this actually in GR. So I have not yet done real tests in general relativity, but in March this year, Boris put a paper on archive, doing some tests with GR. He did some apples to apples tests, and he did a short binary run with the Z4C formulation of the Einstein equations. And I just kind of highlighted a sentence there from his abstract, which shows that he saw an order of magnitude reduction in the phase error for some of these tests for the metric components. He was using a 6-order compact scheme, and anyway, so I think there's some promise as we develop that. There are some challenges which luckily I don't have time to talk about, so I can just pretend to sweep them under the rug. But anyway, Boris, these kind of, you have to look at his figure. That figure on the top right kind of shows some tests he was doing to overcome some of those challenges. I think actually, I'm just going to mention one more thing here. As I mentioned, communication on HPC systems is expensive and it's difficult. So one thing that we're just playing around with, or some of our computer science colleagues are playing around with, are ways to reduce the communication. Now, you can communicate lots of different ways, but at some point you've got to communicate a certain amount of information. We're looking at how do you reduce the amount that you have to communicate. And one way you can imagine, there are different parts of your grid where the precision you use matters more or less. So for example, if I'm near the outer boundary, my grid spacing is like a half, and computational coordinates, I know that I don't have a very precise solution. Do I really need to communicate 16-bit, double precision numbers for every single value? Is it sufficient to use single precision numbers, right? Cut the number of bits in half. Is it possible to find other, even, greater savings? So for example, in some of these regions where the functions are fairly flat, we might be able to approximate them much or quite accurately or sufficiently accurately with Chebyshev components. And then we can maybe send just a few points instead of a lot of information. So we're looking at some different things, basically different ways to reduce that communication. And I think I'm just going to come to my summary and say that I'm excited for this challenge and relativity as we try to keep up with the quality of the scientific data coming from the new gravitational wave detectors. They're going to tell us what that means in terms of targets, I hope, because I want to know what they are. And we're developing Dendro as a way to address some of these challenging problems, and the code's available. And if you'd like to learn how to run it, I'm happy to talk with you and help you get started with that. And thank you.
A couple minutes for questions, Carlos?
Yeah, I have a brief question and comment. If we come back to this snapshot where you had shown kind of the grid for Q equal 116. You had a movie before, but for an animation. Okay, so can we see this as kind of refinement levels? This structure, and how many of those you would need to solve this Q16?
Not necessarily. This is just it's a run that we did. I didn't try to ask, could I cut it the refinement in half? Or is that what you're asking?
Yeah, I mean,
this is not necessarily the minimum number. This is just from a run that we did.
I associate this, I mean, the density of the grids there, you have 1, 2, 3, 4 in the angle refinement level. So how many of those you need to solve
for Q16? Are you asking for the minimum number? Because I don't know that. But
I mean, what you will need to have a comparable accuracy to Laser. You were comparing with.
This is, I think, a factor of 2 finer than what Joseph used with Lazev.
I mean, we should use
for an
around
equivalent
12 refinement level.
This is, so we count refinement levels. We don't start with like a base, you know, a grid of 100 points or something, or 80 points cube. We count the refinement levels from 0, like 2 to the 0. And this was, I don't remember, this is probably like 7, probably at least 18 levels, but I don't remember the exact number.
Okay, that was my short question. My short comment is, the gauge, the lots resolving,
Mhm.
the gauge waves of the lots.
Yes,
So let me highlight here the word gauge. So, yes, there are waves, but they are gauge.
mhm.
So, do we need, I mean, if we can resolve it, okay, that's fine. If they are too high frequency, you under resolve them. I think you okay, because this is like filtering or
Yeah,
smoothing.
yeah,
And I think I try to interpret what you were saying, because when you tell the waveless system, okay, don't go for it and try to resolve this exactly. You are under resolving, and you are still fine because they are engaged.
yes,
For the physical quantities, of course, I mean, they can contaminate with air and so on, but you don't need to beat them to death to have something
Yes.
meaningful as every.
yeah.
So that was my interpretation of.
Yeah, that is exactly right. And the challenge that we have is, you know, as I would like to be able to tell the wavelets, just go out and do the right thing, right? I don't want to restrict you too much, because you might find something important to refine on. But then it's, how do you tell it, well, ignore that little blip and keep that little blip in there, and so that's kind of the issue that we're trying to find a good answer to.
Okay, well, we have a discussion session this afternoon, so maybe we can talk more about some of these issues. But let's thank the speaker again.